So I am happy to introduce the second speaker of this session, Professor Grigori Amosov, and he will tell us on perturbations of quantum dynamical semigroups by operator-valued measures. So please.
Thank you. This is a great pleasure for me to participate in this conference, and it's not for first time. And I am very grateful to the organizers to give me this opportunity. I would like to discuss maybe the most general approach to perturbations of not only semigroups but also groups by means of operator-valued measure, and not only for operator-valued measures but also as cycle perturbations. This is of great interest for me, not only for this time but during many years. And I would like to discuss all aspects of these perturbations, and maybe I can find some connections between these perturbations, and what is a problem, what problems can appear here is also of my interest. Suppose we have some group of perturbations, the group of operators in Banach space X, and I suppose that the generator of this group has some domain belonging to X, and since I suppose that tau sub T is continuous in some topology in T, so the domain should be dense in the same topology in the Banach space X. And I will perturb this semigroup or group such that I will take another generator C equals A plus B, and with some bounded operator B. Moreover, it is of interest, and it is some special case that should be explained at first. If B is one rank perturbations, but I suppose that although B is a bounded perturbation, the other generator C has another domain, doesn't is not coinciding with the domain of A. It's interesting that although this is this gives us many opportunities to define C, changing the domain, we have well-defined perturbed semigroups or groups. And for example, if we take not generators but co-generators instead of A and C, we can take co-generators that are Cayley transforms of generators. Then we have, instead of unbounded generators A and C, we have bounded co-generators, and we have maybe bounded or moreover one rank perturbations of co-generators, and we have only one possibility to define a perturbation. Nonetheless, this possibility belongs to the case of defining perturbations for generators. Nevertheless, this is this possibility is corresponding to the perturbations changing the domain of a generator, because from all of this perturbation we have surely the perturbation that is not change the domain. It's not the case of bounded perturbations for co-generators. And I was inspired by two papers. One paper is by Anton Baranov and Dmitry Yakubovich. They considered perturbations not groups or semigroups, but rather only operators of the form C equals A plus B with changing the domain, and it was inspired me to think about perturbations of generators. And also this problem was considered by Alexander Semenovich Kolev, who introduced to define perturbations by means of operator-valued measures. And so we, with Yegor Baitenov, considered this approach. Rather, we take together all these approaches and about measures and about perturbations changing the domain. And so I should mark here that due to Kolev approach, we can consider non-standard dynamical semigroups in the sense that semigroups that have not the form of Gorenika-Sokolovsky-Lindblad, and because of some singular things concerning the changing of domain. What is it? We suppose that we have a measure, not a measure by the form of Всеволод-Сагбаев that is not sigma additive, or maybe finite additive, but normal measure on the real line. And we suppose that this measure is covariant with respect to the action of my group tau sub t. I should remark that although the initial tau sub t is a group, I suppose that the perturbed version of tau sub t can be defined only for positive t, so it's a semigroup. So if our measure, operator-valued measure with values belonging to the Banach space X, this measure is covariant in the sense that you can see on the screen, then you can consider the integral equation depending on this measure, and if you can resolve this equation, then the solution is a semigroup that can be named a perturbation of t sub tau sub t by the measure m. We name this perturbation by a perturbation by a measure, or a perturbation by covariant measure. And if you picking up a measure such that it's not have derivative in the zero for t equals 0, you can rule with a new domain for a perturbed semigroup tilde sub tau tilde tau sub t. So I give a few examples that one can prove in this direction. It appeared that there exists a limit in t tends to 0 of this action for in the not in the space X, but for conjugate space, and this limit exists not for all phi from conjugate space, but for some domain, also domain that is weak star dense in the conjugate space. And so we can change the domain of C in such a way. You see that the domain of the generator corresponding to the perturbed semigroups is not does not coincide with the initial domain for the initial group tau sub t, and this domain can be changed, although here also can be find here one can find also if this limit exists and m really it corresponds to the case when m is absolutely continuous with respect to the Lebesgue measure, and in this case, surely you have that the domain of C is the same. Nevertheless, you can change this domain by means of the measure. It's quite important to give some examples, concrete examples in which you can recognize how it works for some special cases. Suppose that our Banach space no more that the Hilbert space L2 on the real line and tau sub 2 the semigroup or really the group of right shifts. If you have only positive t, you have the semigroup, but because we have the entire line, it can be extended to the group of shifts. I mean that positive t are associated with shifts to rights. And I can define measure. So because measure our measure has values in the operators on X, so M is a linear operator on the Hilbert space H. We can define it as follows. Take an element eta from H and M from the segment S R, apply eta equals the scalar product eta and psi 1, and this product multiple the index function of interval SR. I mean that it equals to 1 if, oh, sorry, maybe it's better to write ESR is such a function in a Hilbert space that equals 1 if it's from SR and 0 in the opposite case. And then plus the scalar product of eta xi2 and the integral of SR eta sub tau xi sub 3. You have really, one can check that this is a covariant measure with respect to the action of tau sub t, the group of right shifts. And really one can show that all other measures in the abstract Banach space can be of this form. Nonetheless, it's interesting that if you take 3 different vectors for psi1, psi2, psi3, different vectors, so you can obtain different perturbations. From these perturbations, you can see there are rank 1 perturbations preserving the domain. Nevertheless, if the first term here exists, then the perturbed semigroup but changes the perturbed semigroup changes its domain. Another example. It's not all example. For example, sorry for such English. Nevertheless, if you take the Gorinets-Kosakovsky-Sudarshan semigroup, you can consider it also as a perturbation by some measure. It's also some example, but I cannot give all possible example. And here I suppose that X, the Banach space X, is the Banach space of all normal states on the algebra of canonical anti-implementation relations. It means that you have bounded operators A of F and A star of G, and that can be named annihilation and creation operators of some states F and G from one particle Hilbert space H. These operators X not in H but in antisymmetric Fock space F sub A over one particle Hilbert space H. Then we can consider some antisymmetric vectors from the antisymmetric tensor product of n copies of H with the operation of out multiplication F lambda G. Then you can consider such rank 1 operators in fermionic antisymmetric space, for which we can define the operator delta in such a way that it acts only on rank 1 operator, such that you erase one index J from this auto multiplication of different one particle states, and you can define in such a way our operator delta. Then you can consider a measure in such a way that M, the measure of the segment SR acts on the rank 1 operator Fg as an integral, including the action of delta operator from the previous slide. And then here tau sub t is a second quantization of right shifts I considered before. I mean that it acts by as a shifts on each one particle vector. And this is also a covariant measure, covariant with respect of the action tau sub t. And finally, I can consider another approach to the perturbation change in the generator, the domain of generator. This is so-called cycle perturbations. You can take a composition of action, the initial semigroup tau sub t, and some set of operators W sub t that we can call a cocycle for semigroup tau. So if we forgot about what is tau sub minus t, and we obtained that if this cocycle property is fulfilled, then tau tilde tau sub t is another semigroup. And here I should remark that to define this tau sub minus t, I should think about tau sub t as about a semigroup possessing an extension to the group. Here I inspired by the works of William Arvidsson and Rajaram Abhat, and I not only will take cocycles, will define cocycles, but also I will define the so-called Markovian cocycles possessing additional property. I suppose that our Banach space is Banach is a Banach space of all bounded operators in a Hilbert space H, and H is generated by subspaces H sub t, and for these subspaces we have some group S sub t acting in H such that this group S sub t shifts our subspaces in such a way as here indicated. Then we can define a group tau sub t, taking sandwich x on the left S sub t and on the right S sub t is a star. Then I can take this is another letter W, not W small like before, but W capital, because it's not the operator in the Banach space B of H. B of H. It's operator in H, like ST. Then I can define such a set of operators with additional property that I associate with the name Markovian. And I can here now I can define real cocycle W small sub t from W capital sub t. W small is the operator acting on B of H, while WT capital is the operator acting on H.
Grigori, you have 2 minutes.
Yes, I know. Thank you. And so this is my last slide. I can define a perturbation by means of a Markovian cocycle, and this approach is connected with the approach of a perturbation by measure, because really Markovian cocycle gives us a solution to the integral equation I was starting to show you. And this is the same, although it's not the same, although the limit in the zero count size for WT and M, nevertheless, M is really is covariant measure. It is not the same as this Markovian cocycle. So this is only another way to think about the solution for integral equation. That's all. Thank you.
Thank you very much.